Welcome to the 61st Design Automation Conference. This particular presentation today is going to be focused on chiplets. I hope everybody's in the right place. Let's get started and be respectful of all of your time. My name is Tom Hackenberg, and I'm with Yole Group. We will first go through a little bit of an introduction. Then we're going to go through what chiplets are and why they're important. We'll do a little bit of a presentation of teardown examples to show you that chiplets are real. They're currently being used. We'll talk a little bit then about some market data about why chiplets are important to the future of the semiconductor industry. And then we'll give a little bit of an introduction to why that's really important to design automation and the software tools that many of you are here to either present about or learn about. So moving forward. Just a really brief introduction to Yole. We are about 25 years old. We have offices throughout the world. We have about 180 supporting roles in China, in the US, in Europe. Our main focus is the reports on technology and the markets surrounding technology in the semiconductor industry. We do teardowns, we do advanced packaging, we do market reports on processors, on optics, on RF, on new materials. All of those things are the focus for Yole Group. If you have further questions, I recommend that you go out to yolegroup.com and take a look at us. This particular slide is for those of you, for our audience who couldn't be with us here today. Just an introduction to myself. I'm a principal analyst at Yole. I've been doing this for about 17 years. As I said before, this particular presentation is focused on chiplets, the market around chiplets, some of the design considerations. So, why chiplets? Well, first of all, Moore's Law is the lifeblood of the economic and technology trends in the semiconductor industry. But Moore's Law, as we all know, has had a lot of press around it recently about how Moore's Law is dying or about how the semiconductor industry is going to become a commodity. All of those things have an element of truth, but are very misleading. So as we see from the chart on the left, we have the growing number of transistors on a chip as the traditional progress for the performance of the microprocessor industry. We have a number, more recently, to alleviate the problems with the growth in transistors slowing, we have multiple cores going on chips. But none of these things are progressing, or they're reaching limitations in progressing the performance value of the processor industry. So, from a manufacturing point of view, the costs of manufacturing a transistor has actually been going down over time. So this is sort of balanced out. But we still have a design cost and a barrier coming up for manufacturing of semiconductors that involves the design costs and physical limitations that prevent the future of Moore's Law being the only consideration for the improvement of performance in semiconductor solutions. Not only is the design cost going up, but we're actually reaching both technical and economic barriers. Eventually, if the size of the system with multiple transistors and multiple cores gets too large, we're going to be reaching the limitations of being able to manufacture based on the chip size is too big for the reticle. And that's going to be a huge impact. If you can't make your system on chip, your large heterogeneous solution, small enough to be able to manufacture, then you're not going to market. So in a large heterogeneous monolithic die, there are some key challenges. Number one, the die, as we just talked about, is growing too large for you to be able to manufacture in the equipment that is currently producing systems. And I'm mainly focused on processors here. Initially, the chiplet market is purely a processor-driven market, but this information that you're about to hear about will extend to other types of semiconductors that may be more complex down the line. ASIC solutions all may have advantages to being able to break it down into more independent functional bases. So the integrated features and the materials don't miniaturize as evenly on a large monolithic solution. So if you have a mixture of memory, you have a mixture of processor logic, you may even have some analog or RF components, or desire to bring in optics to the chip directly, you're limited in a monolithic chip basically by the least common denominator in terms of process geometry. So you cannot optimize for the specific function as well as if you were doing a single functional chip. And finally, the number of tape outs is, as your system on chip gets more complex, if you want to be able to service a broad range of products that may have some advantages for your customers to do entry point to more complex system solutions, you may want to vary the amount of memory on it, you may want to vary the I/O on it, you may want any number of reasons for your system on chip to have maybe 4 or 5 product portfolio items for the same family of system on chip. If you're doing that as a large monolithic heterogeneous die, you're having to redo a tape out for every one of those, and that creates cost, right? And time to market issues. Introducing chiplets as a solution to what is happening in the monolithic die world, in the heterogeneous growth, chiplets enable you to, there's no longer a need for the large die that may be too large for a reticle, because now you break it down into a functional die and you can produce many smaller dies that easily fit into a reticle. Also, with the smaller dies, there are yield benefits. With smaller dies, you can take more advantage of the wafer, less waste on your wafers. And in terms of yield, if a small functional value of the final chip solution is defective, then that's much less cost to replace that smaller functional chip than it is to replace an entire system on chip solution. So in terms of waste, in terms of yield, the chiplet technologies are going to have a huge advantage in terms of keeping yield costs optimal. And then a number of as we discussed before, in terms of number of tape outputs, if you only have to vary one manufacturing process for the I/O, or you vary which high bandwidth memory solution you add to it, am I putting on 8 or am I putting on 16? All of that's just an after-the-fact choice. A number of tape-outs isn't required for an entirely new system-on-chip solution. You just add that to the advanced packaging solution. So as you can see on the left, we've been sustaining Moore's law for quite some period of time at a nice, what appeared to be a linear rate. But we were just sort of at a tangent where we are now approaching physical and economic limitations that are stymieing the growth rate simply based on Moore's law. As we move to a chiplet economy, all of those limitations that have to do with chip size and the economics of the larger heterogeneous monolithic chips as a solution to producing more performance are now have a solution that can start to get us on back on track to where we were with Moore's law. So, well, what is a chiplet? Well, in terms of building a design based on chiplet solutions, there are two main paths that are currently being used. We're taking what exists as a platform for a large monolithic heterogeneous die and breaking it down into its functional components. This is what the top path looks like. Then there's also taking functionally smaller or what is typically a very complex heterogeneous die in a smaller package that will still fit into a reticle and actually mirror that heterogeneous solution connected by an interposer or connected onto a substrate as one die or one processor solution, as we have an example here from the Apple M series. So where and why is what are the economics of this chiplet? Well, we've done some research and some analysis here about why chiplets aren't the solution for everything, and when are they going to become the solution for most things. So one of the things you have to understand about chiplets is I'm not here to propose that chiplets are going to solve all the problems. I'm here to tell you that there is a point where the die size and the complexity of the die leads to a point where the manufacturing costs tend to be less when you move from a large monolithic to a chiplet-based design. And in this graph, we see that it starts from a manufacturing side, we estimate just short of around 300 millimeters squared. And that is because there's a crossover. You're actually adding expense with the chiplet design in the fact that you have to design some sort of interposer, some sort of substrate, or some way of connecting those chips. And that has an overhead. And there may even be a little bit of a layout overhead as your solution may meet a common interface strategy that is industry standard. Whereas if you have it as a single monolithic die, you can basically design whatever routing paths you need to be optimal. So there is a trade-off there. And in terms of the die interconnect, there are some packaging costs surrounding a chiplet-based design versus a monolithic design. So there are costs involved. So it means that there is going to be a crossover point where those costs are less than the amount of money that you're losing based on yield, based on the tape outs, all of the other things associated with highly complex heterogeneous dies. And then on top of this, it's not just the manufacturing costs. All of you are here today at the Design Automation Conference because there are design costs associated with this as well. So in terms of being able to do tests, to be able to do design in software, you're going to have to adjust your complexity of the design automation software to accommodate this trend. And that costs money as well. You want those customers to recognize that there is value in your newly chiplet compatible design automation tools. And so we did a second analysis to incorporate design costs, and we find that somewhere in between 400 and 500 nanometers square, we still see chiplets going to be the optimal solution in terms of total cost of design. And then ultimately down the graph, this graph doesn't take into account that there's still the physical barrier of when the large heterogeneous die becomes too big for a reticle. Now you're talking about equipment replacement for manufacturing, which is just not going to happen. Okay. One of the main drivers for this particular trend is data center solutions. And we've already seen companies pioneering the chiplet manufacturing from mainly in the data centers. So this is an example of teardown for a data center solution. We can see HBM modules. We can see the SK Hynix memory, Samsung memory choices. We can see the GPU from TSMC's 4 nanometers. Key here is that you can optimize each of these components in the process node that any given company can optimize that solution. So if you need 28 nanometers for memory, do it in 28 nanometers. If you can do the GPU in 4 nanometers, do it in 4 nanometers. If you can do the CPU in 2 nanometers, do it in 2 nanometers. Optimize each of these functional values in whatever process node it is, and then with the use of the chiplet-based platform, you can bring those all together in an optimized package. Another example of the data center solution, this is a Google TPU version 4. So it's not just the standard processor vendors. We also have hyperscalers, each out there doing their own AI acceleration or other data center graphics acceleration on their own chip solutions. They are all moving to chiplet-based technologies. So generative AI gets a lot of news lately with GPTs from various companies. These are huge consumers of semiconductor real estate in terms of processor demand. Not only do we have multi-core solutions for the CPUs, some graphical interfaces, and we see the evolution here where they've been graphical training solutions. Now, even in the training solutions, we're looking at servers moving to ASIC AI acceleration solutions that are more efficient at a given generative AI acceleration or an LLM's acceleration or even some other AI acceleration like a browser search. All of that can be done more economically by doing one basic platform and then picking and choosing what AI acceleration you need to do for that particular platform. So here's kind of a broad spectrum view of data center AI timeline. You can see a number of players in here who have already have data center heavy-duty heterogeneous data center solutions that as of current launches in 2024 are almost all going to a chiplet-based design. So data center is not the only application that is demanding we move to a chiplet-based design. We're already seeing chiplet-based designs in PCs in the form of AI PCs. So as you can see here, we have a substrate with the CPU and GPU, but an HBM module or an PCH, the the platform control center, which takes the place of our older Northbridge, Southbridge type solutions. So instead of having a Northbridge/Southbridge on a motherboard and then having to worry about whether the CPU is or is not compatible with that particular motherboard, we're now seeing that put as a chiplet-based solution on a single processor. Not only Intel solutions, PCI to AI, or PC to AI PC is an AMD-based solution as well. Here we have a cross-section of the solution based on chiplet-based design. We have the memory caches that can be customized for any particular sub-function of a product line. Apple has its own version of the chiplet-based design strategy as they've moved into the M series of processors all the way up to the Pro series. When you reach the Pro series, Apple has taken basically a single M core and used an interposer to basically duplicate that for purposes of being able to fit within a particular reticle size, and at the same time providing more resource and better yields. So it's not going to stop in the CPU world. It's not going to stop in microprocessors for servers and for PCs. Here we're giving you some free market related data on where we think chiplet-based design is next going to penetrate the fastest. So obviously you see a huge penetration in the data centers, almost taking over data center solutions. We're seeing a rapid move from standard PCs to PCI, PCAI, and then we're going to start seeing that same dynamic moving into smartphone solutions as we start now on the age of having large language models locally on the smartphone. You're going to need bigger and better processors. When Apple released its latest version of the OS and said its new AI series processors or AI integrated Siri technology would only work on iPhone 15 or later generation, 15 Pro and later generations, well, it's because there's just not enough memory on the integrated into the prior solutions. They use an integrated memory solution, so you can't just take an older iPhone and produce it with more memory. So as the SoC has to support new ideas, new technologies, chiplets become more and more attractive, even outside of the CPU world. The thing to look at here, I want to bring your attention to, is it looks like there's really a very small line there for the opportunity value for smartphones. But look at the y-axis in terms of the number of solutions that we're talking about. In the data center world, we're looking at 25 million unit scale. In the PC world, we're looking at a 400 million unit scale. But when we look at the unit scale of the smartphones, we're up to a 2.5 billion unit total available market. So even just a little sliver of that market is a huge impact on your design automation tools requirements. And then outside of those compute space, automotive is a next generation target as we look at drive platforms enabling advanced driver assist systems, centralized domains, zones of control within the vehicle. Those are no longer exclusively supported as an MCU solution. A lot of the vision and pathfinding and reasoning solutions are requiring these much higher level heterogeneous processor solutions, and companies like NVIDIA are targeting automotive drive platforms for this very reason. Outside of that, there are some additional markets that are a little bit farther into the future: defense and aerospace, medical, even some consumer products in terms of set-top boxes or televisions may benefit from this chiplet evolution. So I'm here to focus your attention back onto design automation. That's why everybody's here. In order for you to move along with this evolution, your design automation solutions have to take into account that the ultimate package may not be where you're starting from in terms of designing a die. The design of that die may ultimately go into a package that you can either ignore and say the die passes all of the verifications independently. It's proof of concept, and whatever you may do for a single die may ultimately wind up in a package and fail the entire package because it created hot spots or it created stress factors. There are a number of reasons why an individual die as part of an advanced package may cause the ultimate package to fail. So as designers of software and design tools, it's very important that you are moving towards the future of a chiplet-based economy so that you can develop tools that say, okay, we're going to start with the end package in mind. We're going to develop into our tools the ability to interface with standard bodies like open compute platforms or UCIe, or potentially a market-dependent strategy like DARPA. So you need to be able to accommodate for the interposers or the substrate. You need to be able to accommodate for how that's ultimately going to be packaged. I've already seen some tools at this conference that are already on the way to that, to doing digital twins from all the way from the beginning of the design factor, all the way out to trying to predict the thermal resolution when it actually becomes packaged with other design chips. And that's what you're going to have to do to accommodate this new chiplet-based economy. You're going to have to take in mind all the way from the very beginning that it's moving to a package solution that you may have to accommodate for in your layout. I also heard in the conference that Intel is now, or Intel Foundry with EMIB is now supporting platform agnostic solutions across the board where each individual chiplet component can be of a different process node, can be from a different manufacturer, and they are willing to work with you to try and develop that on an EMIB platform. So we are definitely moving to an open commerce platform if somebody like Intel can say, we're supporting the open platform solutions so that this chiplet-based economy is here, it's real, it's going to be cross markets, it's going to be cross companies, and it's definitely going to be something that you need to take into account as you develop your future iterations of design tools. These are complex solutions. Developing AI into your design tools may be the next stage or already in process. These are all why I'm here to present this to you as design automation professionals. You need to understand where the semiconductor market is going in terms of manufacturing. And with that, just to summarize, the desired pace of integration is moving faster than scaling. We are definitely at a point where you can just not keep shrinking the transistors to solve your problems. We've already moved into heterogeneous solutions, and even that's moving towards a cliff with the large manufacturing requirements of heterogeneous processing. With more advanced nodes, the design costs are growing exponentially. Monolithic SoCs are capable of high bandwidth intra-chip solutions, but there are also design tools that are necessary and some currently available to increase the bandwidth interchip to accommodate the chiplet-based economy. So there's definitely a growing incentive for using smaller dies, whether it's yield, whether it's accommodation for reticles, whether it's performance optimizations per function. It's definitely an application where there are multiple reasons why it's becoming optimal. And taking that all together, we definitely are moving towards a chiplet-based economy. Is this going to replace every semiconductor solution? No. As we saw previously, there is a point where monolithic solutions are still the most economical, they're still practical. When you don't have a wide variety of process nodes that you need or a wide variety of functions, when they're in a small package already, there's no reason to add the expense of chiplet-based design. So your tools will definitely need to accommodate both monolithic and chiplet-based designs. So with that, I will open the floor for questions. If you have any, there are microphones at the center. If you'd like to ask a question, please step up to a microphone.
That was a very nice talk. And just a quick question. So when you have interposers to connect die to die, you can't have 128 wide buses running around. So that's where they're using SerDes?
Yeah.
Oh, okay. And
it's a combination of solutions depending on the individual needs of the heterogeneous SoC. But SerDes is definitely when you look at there are standards bodies that were presented up here, OCP, UCIe, definitely look at the characteristics involved in those standards practices.
So given the different challenges of a 2.5D integration versus a 3D integration,
Yep.
Can you speak to whether there may be an advantage in focusing more on one versus the other to accelerate the 3D, the third-party ecosystem so that everyone can take advantage of chipletized design?
Yeah, so there are definite distinct advantages for either 2.5D or 3D. A lot of that has to do with stress factors or heat factors, right? So if you're having a stress or a heat factor that prevents you from doing an optimal 3D stack, then maybe taking that one piece that's creating the problem and moving it into a side position in a 2.5D stacking solution is the way forward. And in the future, that may not be the case. Our tools may get better, our layouts may improve, where 3D becomes more universal, but right now, there's still definite design considerations, and it may even be just the height of the chip itself that is a consideration in terms of being able to package it appropriately.
But do you think we should focus on one versus the other more heavily? Should the EDA vendors maybe focus on 2.5D more, enabling that solution, because perhaps the challenges of 3D are so much more enormous that if we could get a 2.5D baseline, get people doing chipletized designs more ubiquitously, might there be an advantage to that?
Initially, probably, but ultimately, if you are going to focus too heavily on 2.5D, you may be behind when the 3D solutions become the more prevalent market space. So yeah, you're right in that if you want to go to market now, your optimized customer solution might be the 2.5D space. But as we saw, based on just interposers or HBM is a 3D stacked, if you want to be able to address those markets immediately, then you may also have to incorporate tools that address 3D stacking.
Okay, thank you.
I stepped in late, so I apologize if I missed this. You showed impressive growth for the chiplet economy and CPUs. Did you analyze the same for GPUs?
Yes, we did analyze the same for GPUs. It's interesting that Hong said at one point a couple of years ago that this whole chiplet thing, don't worry about it, our monolithic heterogeneous die is still got a lot of legs moving forward. And the next year they immediately went to a chiplet-based design. So NVIDIA and AMD are both the primary GPU vendors. Both of them have moved to chiplet-based solutions. One of the examples given up here was NVIDIA die. But if you want to see more teardowns of different dies, GPUs, for example, that's why I recommend you to go to Yole Group and see what we have in our teardown inventory.
And do you predict similar growth rates for GPU as you showed for CPU?
Yeah, so absolutely, GPUs are especially moving towards a GPU along with an applications processor unit, along with an AI accelerator function, possibly a security function. They're moving more heterogeneous than exclusively GPU.
And those are co-packaged?
And those are co-packaged.
Thank you very much.
Okay.
Hi, I'm with Esperanto, and we're designing chiplet-based AI accelerator chips. And right now we're look at using UCIe, which is the Universal Chiplet Interconnect Standard. But what I understand from our technical team is that this is mainly just specifying the physical interface, and that the protocols are not standardized.
Right.
So that seems to me to be a big barrier if you want to actually tile chiplets together from varying manufacturers. There's got to be a common protocol to communicate.
Right. So I've heard the same thing, and I'm not a member of the UCIe Technical Advisory Board or that group. There's also the bunch of wires-based solution that's being promoted by the OCP. They are not exclusively independent. You can use both standards bodies for ultimately developing the solution, or even other standards bodies, DARPA or whoever your particular target market is. These standards are relatively new. They're still being developed. So I've heard that the UCIe standard is primarily targeted where you're already in system developments that use PCIe. It's a real accelerator to time to market. Your engineering staff typically can adapt a lot easier to UCIe standards when you're talking about data center, when you're talking about PCs, when you're talking about other types of application-based systems that are based on a PCIe platform. But when you start getting down into, say, a smartphone or a drive platform in an automobile, that UCIe might not serve you as well because of the other standards that you need to be able to adapt to.
Thank you.